Welcome to our discussion on the precise definition of a limit. Buckle in, kids. This is going to be a bumpy ride. This is one of those topics that really throws a lot of students for a loop. So don't feel bad if it's a little confusing in the beginning. It will get better, I promise. Okay, we've already looked at limits. We already know basically what a limit is, right? It's asking us to let x get really super close to a certain number, a, and then the output of the function, right, f of x, gets closer and closer to some output number that we call L. But the problem is the phrase close to is too arbitrary. In mathematics, we like to be precise. So this type of phrasing, this type of idea of what a limit is, it's great for understanding the theory of it, but it's really crappy if we want to be precise. So we want to get rid of that vague language and instead try and come up with a precise definition for what a limit really means. And that starts with this example. Let's say we have a function. Let's say we've defined it this way. The function is normally 2x minus 1 for all values except 3. When x equals 3, all of a sudden we're going to let it be 6. Now, of course, that means that if we were to graph this function, it would look something like this. 2x minus 1, about like that, right? It's down here at minus 1. And then it's going to go through at a half, right? My scale's all off. And then over here, let's say at 3, there's going to be a hole in it. And instead of the answer being 3 times 2 is 6, 6 minus 1 is 5, it's actually defined as a dot up there. Okay. So intuitively we can look at that picture and we can see very obviously that as we let our values of x get closer and closer to 3 but don't let them equal 3, then the value of the function is going to get closer and closer to 5. And we've seen examples of this before. But how close to 3 do we have to actually get, right? How close do those x's have to actually get in order for the output that we get from the function to be, let's say, within 0.1 of 5, so somewhere between 5.1 and 4.9. Well, the distance between our value x and 3 can be written as the absolute value of x minus 3. That is what distance is. I know you guys have probably thought of the absolute value function as just this thing that makes things positive, but what it really is a distance function. That tells us the distance between 2 points. And then, of course, the distance between the function and 5 is also an absolute value written this way. So if we want to figure out how close x has to be to 3 in order for the function to be within 0.1 of 5, then we're asking, okay, we want the distance between the function and 5 to be less than 0.1. If that's the case, then we want the distance between x and 3 to be less than how much, right? What do we have to set it to in order for this to work? But we always have this caveat that it can't be equal to 3. Well, if the absolute value of x minus 3 is greater than 0, right? If the answer we get from this is always greater than 0, then that means x is never equal to 3. So we can take these two phrases and put it together as one compound inequality. And now we have the makings of the precise definition of a limit. Now let's look at some stuff further. You'll notice that if we substitute in the formula for f of x, 2x minus 1 minus 5, do the math, 2x minus 6. Now, hey, wait a minute, 2x minus 6, I can factor a 2 out of there. And yes, you can pull the 2 completely out of an absolute value, right? It would have been 2 times the quantity x minus 3 on the inside, but the absolute value of 2 is still 2, so that comes out on the outside, nothing changes. And so, when we're saying we want the absolute value of f of x to be less than, f of x minus 5 to be less than zero point 0.1 by substitution, as we've seen right here, that really means that this stuff is less than 0.1. And then if you divide both sides by 2, you get x minus 3 absolute value is less than 0.1 divided by 2, which gives you 0.05. And so before, when we had, this hasn't changed. We'll go up and remind ourselves, right? That's still what it said. If the difference of this is less than 1, we want to find this delta. This is the Greek letter delta, such that the absolute value of x minus 3 is less than that. Well, we just figured out that the absolute value of x minus 3 has to be less than 0.05, so just set delta to be 0.05, and then that means that the function will be within 0.1 of 5, right? So as long as we're in a neighborhood that is smaller than 0.05 away from 3 on the x-axis, that means the answers we're getting out of the function will be within 0.1 plus or minus of 5, right? They'll be within 5.1 to 4.9. Now, that choice of 0.1 was kind of arbitrary. We just said, let's make sure that we're within 0.1 of it. Well, what if we want to be even closer? What if we want to be within 0.01? Well, if you go back and look through those steps, you'll see that the last thing we did was we had the absolute value of x minus 3 was being divided by the original number, 0.1, and then divided by 2, right? So it was less than that divided by 2. So now if the original number is 0.01, we divide that by 2 and we get 0.005. But what if we want the original number to be 0.001? Then when you divide that by 2, you get 0.0005, and so on and so on and so on. So these numbers, these arbitrary numbers that we started with 0.1, then we went to 0.01, then we went to 0.001, they're getting smaller and smaller, right? These are considered our error tolerances, or how far off we can be from that limit L that we're trying to, zero in on, in this case, the number 5. And right now we're taking arbitrary numbers. We're going to see that when we go to the precise definition of a limit, instead of saying, well, it has to be within 0.001, we can just say it has to be within an arbitrary amount. And that's what we do here. We say, instead of it being some number, we're just going to say, hey, you know what? We want to see if this will work for any number, no matter how small it can get. We've seen that it worked for 0.1, 0.01, 0.001. I bet you I could do it again for 0.001, and I bet you I could do this all day long and have 0.00001, and it would still work. Well, let's generalize it a little further and just say, how about any number, and we'll call that number epsilon. Don't let the epsilon make you confused. It's just another Greek letter that just stands for a number. So now instead of a specific number, we're going to say we want to be able to prove that the distance between the function and what we think the limit is, right? Because remember here, this is just what we think the limit is, L. The distance between the function and L is just going to be less than some arbitrary number epsilon. Well, as we saw in the previous work, that as long as we set this delta number to be epsilon divided by 2, right, as long as it was half its size, then it always worked. Now this is just for this specific function. We're going to get a different equation for delta with every new thing, but the idea is still the same, right? This picture shows what's happening. We had 3. We have a neighborhood around 3. If you go 3 minus delta, right, however big delta is, if you go that distance in both directions, you go up, you project it, and you get this neighborhood around 5. Well, you just want to make sure that however small you make this neighborhood around 5, so if I shrink it down, and I now want my neighborhood to be here and here, then you can see that, oops, bad drawing, sorry. Boy, I just cannot draw. All right. Let's try this again. You can see that if we shorten our neighborhood, it just around 5, it just makes the neighborhood around 3 smaller. Which brings us to the actual precise definition of a limit. By taking these values of x that aren't equal to 3 but are small enough that they're in this little tiny interval of plus and minus delta around it, right, in that little tiny interval around 3. If we take those intervals, we know that we can make the values of f of x lie within the interval, the small little interval that is epsilon wide around 5. Again, don't bother with the whole delta epsilon thing. This just means that they're two arbitrary numbers and they're not necessarily the same, which is why they're given different letters. Okay, so think about the picture. If you're within a small little neighborhood around 3, then those projected answers, right, that you get out of the function are going to be within some interval around epsilon. And no matter how small you shrink that epsilon neighborhood around 5, you can always find a corresponding little neighborhood around 3 that will keep you within that range. And that's the definition. If we let f be a function defined on some open interval that contains the number a, that's just saying let f be a normal function that's defined everywhere on some open interval. An open interval just means that it's not defined from 1 to 3 with closed brackets, it's from 1 to 3 on open brackets, right? Just doesn't mean it doesn't have hard endings. And that interval contains some number a. So it's defined on an interval around a. Except possibly at a. Right? We're always going to say this over and over and over again, that when we're dealing with limits, the function never has to be defined at the value a that we're dealing with. That's always key. Sometimes it is defined there, but it doesn't have to be. Okay, so if we have a function that's defined around a, then we say that the limit of that function as x approaches a is L, and we write it like this, right? Limit is x. That's all normal. We've seen that before. But now we're going to add this little extra bit that says this is true if for every little epsilon you can find that's positive, right, of epsilon greater than 0, there is a corresponding tiny little number delta also greater than 0, such that if the area between x and a is less than delta, if the distance between x and a is less than delta, then the distance between the function and L is less than epsilon. It's back to that picture. If you're within delta of 3, you have to be within epsilon of 5. Right? If you're within delta of a, you have to be within epsilon of your limit. And that's the precise definition of a limit. If it's making your head hurt, don't worry, it's not that important. Most of the work we're going to be doing with limits really requires us to just algebraically manipulate things and move them around. And it's not a big deal if this isn't really sinking in. You'll get it there eventually. We can restate this definition without all of the jargon and symbols and just think about it in English, right? Since the absolute value of x minus a is the distance from x to a, and the absolute value of f of x minus L is just the distance from the function to L, and since epsilon can be any small number you want, the definition of the limit, as we've seen before, the limit as x approaches a, f of x equals L, that thing really just means that the distance between the function and L can be made as small as you want by just taking a distance between x and a small enough, right? Sufficiently small. So you can get as close to L as you want by just getting as close to a as is necessary. Alternatively, the values of f of x, right, the values of the function, can be forced to be as close to L as we want by taking x close enough to a. So it's a two-way street. It goes both directions. We can also rewrite the definition in terms of the intervals by noticing that the inequality, right, x minus a less than delta, is equivalent to just having a minus delta on one side and a positive delta on the other side. And then if you add a to both things, then you can say, hey, as long as a is between as long as x is between a minus delta and a plus delta, then all of this stuff is true. So you can think of it in two different ways. It's just going to, don't worry, if that, just go with one. Same thing here, we're rewriting the less than epsilon thing in terms of intervals. So we have this little interval a minus delta and a plus delta, and then we have this other little interval L minus epsilon and L plus epsilon. If you understand this picture, that's what's most important. Don't get bogged down on the terminology. Okay, here's a nice geometric interpretation of the limits. We have this number L that we think is the limit. We have this little neighborhood epsilon around that L, right? So it's the same distance top and bottom. We have this A that we're trying to prove that as we get close to A, the function gets close to L. Well, if you look at the kind of intersection of the blue epsilon stuff and the function, you'll see that it actually hits here and here. But because we want the neighborhood around A to be symmetrical, we can't have this distance and then this much bigger distance over there. And if we let the distance on the right hand side be the same size as the distance on the left, then all of a sudden we get values for the function that are more, right? This is further than epsilon away from L. So that's why we have to instead restrict the little neighborhood around A to the smaller of the two. So we use this distance instead of the longer one. It's important to realize that this works for all values of epsilon, right? So if we take this one and shrink it down to this one, same idea, just smaller epsilon, it still works. And you'll still see that the same thing happened here because of the shape of the function, that the left bound was actually further out, right? If we were anywhere over here, those numbers are all going to give you, right, they're going to hit along here, and they're going to give you y values that are within epsilon. But we can't use that same distance in the other direction, otherwise we start to get values down here which are outside the band. So instead we restrict it to the smaller of the two sides, the two sides of the interval. Okay, let's look at an example. We've got some function x cubed minus 5x plus 6. We were going to use the graph of this function to find the number delta such that if the distance between x and 1 is less than delta, then the function is going to be less than 0.2 away from the number 2. That's what all that gobbledygook on the second line is just saying. Remember, this first piece is the distance between x and 1, and this is the distance between the function and 2. Okay, here's a graph of the function. Notice that we can rewrite that inequality that we had originally, this one here, that if we want to get rid of this 2, we have to add it to both sides. But you're like, hey, what's over here? Well, remember that if we're dealing with an inequality and we're saying this stuff is less than 2, it's also greater than negative 0.2. So when you add 2 to both sides, that's if when you ignore the absolute values, it's in between those two. Then you add 2 to both sides, and that's where you get the 1.8 on the left hand side. So we're just solving for an inequality here by turning it into a compound inequality without the absolute values. Okay, so that tells us that the distance, right, the distance of this function, the distance from this function, has to be somewhere between 1.8 and 2.2. So we've got these two horizontal lines at 2.2 and 1.8. and that's the neighborhood around the point 2. Now we just have to figure out what neighborhood around x equals, what was it again? Right? X has to be within delta of 1. Right? So we're finding the neighborhood around x equals 1 that will keep us in those answers. Well, if we had technology, we would move the cursor around and figure out what it was. If we didn't have technology, there's other ways to do it. But you're basically, as far as the graph is concerned, you're doing this. Draw a line, right, down to wherever the x-axis is. Draw a line down to the x-axis. Right here is x equals 1. And this distance, and then this distance, this is supposed to be our deltas. But you can already see from this picture, even with my poor drawing skills, that the two don't seem to be symmetrical, so you just need to shorten it up to the smaller of the two. And that's what we're talking about here. That if you had the graphing calculator or whatever technology, you could see that that interval you get on the x-axis is basically 0.92 and 1.12, but it's not symmetrical. The distance from 1 to the left endpoint is 0.08, and the distance to the right endpoint is 0.12. So you would just take the smaller of the two and do 0.08 in both directions. Right, which is what we're going to do here. We're going to let delta be 0.08. So then we know that if we have a neighborhood smaller than 0.08 around 1, right? The distance between x and 1 is less than 0.08. Then we know the distance between the function and 2 is going to be within 0.2. Here's another example. Let's say we're trying to prove that the limit as x approaches 3 of 4x minus 5 equals 7. And you go, well, duh, if I just plug in 3, I get 12 minus 5, which is 7. Okay, so that works. But yeah, we're trying to prove it. Let epsilon just be any given positive number, just some arbitrary positive number. We need to find a number delta. Right? So you always start with a neighborhood around the function and the limit. Right? You start with epsilon and then you work backwards to solve for delta. So epsilon's arbitrary. We need to find a delta that keeps us in that neighborhood. But if we work with, and this is what you do every time, you work with this piece. You work with the function, right? This is f of x minus L. Work with this piece and see what happens. 4x minus 5 minus L, combine like terms, right? 4x minus 12, factor out the 4, pull it completely out of the absolute value. And now you know that if the distance between x and 3 is less than delta, then by all that algebra we did, 4 times x minus 3 has to be less than epsilon, right? All we're doing is rewriting the definition here with this new piece. This is like a little substitution back in here. Well, if this is true, then this has to be true, right? Divide both sides by 4. And so all we have to do is let delta be epsilon over 4. Because if delta equals epsilon over 4, then by substitution again, this first piece says 0 is less than x minus 3 less than epsilon over 4. And you go, if this is true, then x minus 3 is less than epsilon over 4. And you go, well, duh. So if a is less than b, then a is less than b, of course, right? So that's the whole point. You want those things to match. And that's what we're doing for all of these. That's how you solve them. Now the proof, right, that we're doing here is just plugging everything back in and showing that it actually works. This is what matters, getting to this place, this step, because the type of questions you're going to have is just find the delta that makes this true. We just found the delta that makes it true. Okay? So a nice way to look at these always is to visualize them. We just found the neighborhood around 3 that keeps us within epsilon around 7. Okay, left-hand limits and right-hand limits, as we've seen before, are treated the same way as a normal limit. So if you have to deal with a left-hand limit and a right-hand limit, the same exact definition of a limit works. The idea of the distance between them being less than delta and the other one is less than epsilon, only now we're looking at half of the interval instead of the whole interval. Infinite limits are also very similar. The only real difference is instead of having this piece, which is the same, and then remember the original definition was then we had f of x minus L, the distance between the function and this limit, was less than some epsilon. Well, if we're trying to say that the limit as we approach a becomes infinity, then we can no longer say that the distance between the function and some number is within a certain amount, because if it blows up to infinity, it can't be capped, right? It can't be within a certain amount from some number. So instead we just know that if it blows up to infinity, it gets arbitrarily large, which means no matter how big of a number you choose, the function will be bigger than that number. So we're just swapping out the original thing that it has to be within a certain number with the new idea that it has to be bigger than a certain number. And this is what it means graphically. You can see very clearly that no matter what you choose for m, so if I come along and decide I'm going to draw my new m up here, well, now these lines are just going to be inside those, right? And I won't try and draw those all the way down because I'm horrible at it, but you can see that it's just narrowed that window around A. We can use that definition to prove that as x goes to 0, 1 over x squared equals infinity. So we let m be any given positive number. We want to find this delta such that if the absolute value of x is less than delta, and why is it just the absolute value of x? Well, remember the original thing is 0 less than x minus a, right, is less than delta, and in this case a is 0. If this is the case, then we know the function is greater than whatever m we choose. Well, starting with this, just like before, remember we started with f of x minus L was less than epsilon and did some manipulations. Same thing, we start with this piece, we do some manipulations, so 1 over x squared greater than n, multiply both sides by x squared and then divide both sides by m, and you get this new relationship. Take the square root of both sides, you get this, and you know that the absolute value is less than this, right? These are all true at the same time. So if the absolute value is less than this, then this piece is true. So if we let our delta, right, if we let this delta just be this answer that we got, then everything's true. And this shows that as 1 over x squared goes to infinity, as x goes to 0. Last but not least, of course, if we're doing a negative infinity limit, it's just the same thing, except instead of f of x being greater than some number, we know that it's always less than some number, and that's what you start with, and you work backwards from there. Okay, I'll post some examples to help you guys through with these. You'll see it better once you apply it.